What's the second one? If the second one's red.
9 out of 25.
9 out of 25 plus
Same thing. Same thing.
10 out of 26 times 9 out of 25 for green plus 6 out of 26 times 5 out of 25 for white. Right? So notice it's always 26, 25, 26, 25, 26, 25 in your denominator because it's without replacement. If you were replacing it, the denominator is always 26. But since you didn't, it changes. So we get 180, 210 over 650. 1 minus that, you got 440 over 650, 44 over 65. Whatever that is as a fraction.
Like 6.
0.67.
0.677. Okay. How many decimal places do you do to every question on this test?
3.
I'm sorry, not decimal places.
60.
Significant digits is 3.
3.
Okay. In this case, that's the same thing because of where the decimal point is. So it's 0.677 is your answer, or you can give it exact, which is what I did, which is 44 over 65. Okay.
Which one's better?
Neither.
Yeah.
They're the same. So you can answer exact or to 3 significant figures. Okay, number 1.
Should we give it as a decimal or keep it as percent, right?
Either way, but then it's 67.7%. Yeah, with probability you can do decimal, fraction, or percent. All right, the one at the bottom is like what we did a while ago, so I'll move on because that's what we just did, where you enter the 6 and you do the frequency list and you get the median and mean. We just did that with the calculator, right? Okay, let's find some more probability here. All right, the one at the top, okay? The first part's just filling in. It's like a Sudoku, right? How many boys watch television or pick television? 13, right? Because you have 46 total, so there you go. You got to fill it in. How many girls total were there?
54.
54 to make it total to 100. Then you total up this way or sideways, and this is what? 62, and this up here is 25, and this is 38, right? That's how you fill in the box. Everybody good with that? A, student selected at random prefers to watch television. 38 out of 100. You can reduce it, you can leave it as a decimal, you can make it a percentage, it doesn't matter. Okay, I'd probably just say 0.38. B, a student prefers to watch television given that the student is a boy. 13 out of 46. And that's probably how I would answer it as a fraction. Okay, if we're given that it's a boy, then we're only looking at the 46 boys. So of the 46 boys, how many of them prefer to watch television? 13. All right, get the idea there? It's a pretty straightforward question.
So now this would we have to show our work?
Doing this is showing your work.
Okay.
Notice it says by completing this table or otherwise.
Okay.
So
So why wouldn't you do that one out of the total who like to watch TV, out of 38 instead of 46?
because you're the given, so we're given that the student is a boy. So now we're only looking at the 46 boys. So if we know the student is a boy, then we're only looking at the 46 boys. So you ignore all the rest of your data. Of those 46, what's the probability that the student prefers to watch television?
13, but I mean, why wouldn't that mean of the kids who watch TV, how many boys like to?
Because boys can't.
Because that would be, what's the probability that a student prefers to watch television, or I'm sorry, what's the probability that a boy prefers to watch television given that they watch television? See, you have to think about how you're conditioning the probability. What are you restricting? So it's that given part. So given that the student is, I like to think of it that way because put that first in my statement. It's given that it's a boy. So it's almost like if you have the 100 students in front of you, given that it's a boy, The girls disappear. So now I'm only looking at those 46 boys.
Okay.
Of those boys, how many like to watch television? Just the 13. Okay. If you were to use the formula to do this, the formula would be 13 out of 100 divided by 46 out of 100. See what I'm saying?
Yeah, yeah.
Because the 13 is boys and television divided by just boys. Okay? Okay, so we go on to the next one. It's another replacement problem. Then we're going to get into distributions here in a minute. Box contains 22 red apples, 3 green apples, 3 apples selected at random, one after the other without replacement. The first 2 apples are green. What is the probability that the third apple is red?
22 out of 23.
Everybody agree with that?
Yeah.
We know the first 2 are green. That means there's only 23 apples left. B, what's the probability that exactly 2 of the 3 apples are red?
You just do 22 over 25 times 21 over 24 times 3 over 23. You multiply by 3 because there's 3 possibilities to do that.
That's one way of doing it.
You're good at this.
Let's go back. Let me write down the answer.
So, like, I will think about how
Yeah,
to
we studied this, and like it was just one day.
That was that one problem. I couldn't
Yeah,
do.
it was the one problem he couldn't do, and he
yeah.
spent like forever doing it.
Why are you
and now he got
complaining
really good at
about
it.
probability then? If you get it.
Well, this is the only part I know how to do. Is that how you do it?
He said it was one place.
Well, yeah, but here's what I would think about.
So when it asks for exactly, though,
Exactly.
it doesn't matter what order it's in.
What?
It doesn't matter what order it's in, right?
Sure it does. Order always matters. Okay? If exactly 2 of the 3 apples are red, that means what are your possible outcomes?
You have the first and the first.
You have red, red, green, red, green, red, or green, red, red, right? Now, what Dimitri's saying is the probability for this happening is the same as the probability that that happens, is the same as the probability that that happens, right? Everyone agree with that? That means if I can find one of these and just triple it, then I've determined my probability. So what's this? This is 22 out of 25 times 21 out of 24 times 3 out of 25, right?
3 over
23.
23. Thanks for catching me there. So multiply that and then multiply it times 3 because it's really plus the same plus the same. All right? Now, the alternative would be what's the opposite of exactly 2 of these are red?
2 of them are green.
Or all of them are red, or 3 of them are green, right? So that would actually get into more calculations in this instance. But always think about that. Is the opposite easier to do? In this case, no. So what's your answer end up being here?
0.301.
Okay. All right, I like the next question. The table below shows the marks gained in a test by a group of students. So you got 5 different grades, 1, 2, 3, 4, 5. You have 5 kids that got a 1, 10 that got a 2. We don't know how many 3s, 6 4s, 2 5s. The median is 3 and the mode is 2. Find the 2 possible values of P. If the median is 3, okay, well, first of all, if the mode is 2, then what's the biggest number P can be? 9. Okay, so P can't be any bigger than 9. All right, but if I have 9 here, then let's see, 9 plus 6 is what?
15.
Plus 2 is 17. If I have 9 here, then do I still have a median of 3?
Yes.
Yeah, so P can be 9. Obviously, it's got to be less than that if it's not 9, so can P be 8? 8, I still have 16 here, right? If I let P be 7, I'd have 15 and 15, so what would my median be?
2.5.
2.5. So P can be 8 or 9.
So it's just a guessing check thing.
That's all it is.
Or you could just write 1, 1, 1, 1, 1, 10, 10, 10, 10, 10, 10, 10, 10, 10.
So why would you do that?
Okay, you can ignore Dimitri right now. Or you can just say, look, I have 15, So this has to be more than 15.
Right.
So how is this more than 15 when this is 8 or this is 9?
You're right.
Okay,
We're not gonna
quickly,
do one-
let's do this one. What?
We're not gonna do one at the bottom?
Not yet, because it has to do with,
Distribution.
The mean.
I thought it was a distribution problem at first, is it?
I don't think
No.
so.
I don't think so.
It's really just a group data type thing. If from January to September, that's 9 months, so you would do 9 times 630. And then you have from October to December, which is 3 months, 3 times 810, and then divide it all by 12,
Yeah.
right? It's just like a grouped data type thing, or frequency data, frequency chart almost.
Yeah.
675 is what I got.
What did I do wrong? I did not, I'm dyslexic.
Yeah.
Yep, 675. Okay. All right. This little game show thing here, spin the wheel. This mixes geometry with probability because you got to know how many, degrees are in a circle. So the larger angles here, the ones that are shaded, are 40 degrees. The smaller ones are 20 degrees. Find the probability that a contestant will not win a prize. So there's no prize. There's 6 different sections of 40 degrees each. So that's 240 degrees out of 360 degrees, or 2/3. Right? So probably they will win a holiday in Greece. Well, in Greece you have 2 of the little sections. So what's that? 40 out of 360, or 1/9. Again, you don't have to reduce, but to me it's bad math if you don't. But C, will win a washer and dryer given that he knows that he has won a prize. So if we know you've won a prize, we're now only looking at these 6 small sections. Washer and dryer is 3 of those 6 sections, so it's 1/2. Or you can think of it as 60 out of 360 divided by 120 out of 360 if you wanted to use the formula. But it's 1/2. We'll win a holiday in Greece or a washer and dryer. Okay, well now you're talking about 1, 2, 3, 4, 5, or 100 out of 360, which is what?
518.
Yeah. They kind of get you there because you think you're only going to look back at the prize, but it's not the prizes. It's not 5, 6. It's 5 out of the whole sort of 5 out of 18. Okay. Let me look through real quick and see what other ones.
Oh, tree diagram.
Yeah. Okay, that's good. Tree diagram's good. We'll do number 13. Okay, I'm going to use another sheet of paper here. Real quick thing on a tree diagram to help yourself out. Always make your first outcome an obtuse angle. Okay? Trust me, that may seem simple, but it helps you actually be able to do them later on. Make it an obtuse angle. Okay? And then your second outcome can be an acute angle if you want it to be. Okay. In this instance of a group of 5 students, 2 will be selected to visit United Nations. The 5 students are John, Maria, Raul, Henry, and Susan. They have a tree diagram or a table of outcomes. Find the number of different possible combinations of students that could go to the United Nations. Okay?
And that's just 5 times 4 times 3 times
It's just 5.
You're only taking 2 students.
2. Yeah, so it's like a number of handshakes.
5 choose 2. Yeah.
It's 5 choose 2, yeah.
Yeah.
Which is not 5 factorial.
It's just 5 times 4.
It's yeah. Right.
Oh, yeah, yeah,
It's
yeah.
10 is the answer.
10.
But you just do
I'm
5
trying to
times 2,
picture
because
that.
you're doing 2.
Yeah, I'm trying
That
to do
one thing.
Because like,
But if
easy
it's
probability, when we were younger, you just multiplied all the things together.
Yeah.
And that's what this is.
Multiply all the what things together?
Like, if they said you had three
3 shirts and 4
apples, 2
pairs.
oranges, and 1 banana,
That's
you just
it.
But
multiply them all
you're,
together.
yeah, you're choosing 2 out of 5.
Which
You're
one
not-
choosing
not
2 out of
like-
5? It's not combinations. Okay. The way you would do it with the diagram, which again, this is not really a tree diagram, but you would have this.
It's 2 times 5.
No.
Ironically, that would have worked for this one. 2 times 5.
So should the answer there be 20?
It should be 20. Then why is 5 choose 2? 10.
But isn't it, it is choose 2, choose 5, or 5, choose 2.
Is it 10?
Yeah. You got 5 students.
1, 2,
2 will be selected of this
4 plus 3
examination.
plus 2 plus 1, that's what it is.
1.
yeah, that's 10.
Because you have to take the first thing off of each one, because it's the same thing as one person going with another. It's not the same as, is it, one person going with another person the same as the other person going with that person, you know?
Like John with
Sure.
Maria,
Yeah.
Maria with John.
Yeah,
Like the
same thing.
sequence
Those pairs are the
doesn't matter.
same.
Okay.
So what are we doing?
Just add, just 4 plus 3 plus 2 plus 1.
Yeah.
Yeah. Everyone keeps leaving.
No.
Are you leaving?
No.
Okay. All right. Yeah. It's basically, it's 4 plus 3 plus 2 plus 1. That's the way I look at it.
Or you can just do it.
Or draw the tree diagram. But
Oh yeah, we have to do that anyway.
it says, or a table of outcomes. But why is it not?
Or
Well, the
table
tree
of
diagram, because like, let's say in the first row you have like Maria.
I mean, I understand. I'm trying to figure out why.
Why is it 10?
No.
Because there's 4 possible outcomes for the first one, and then you can't, then one gets taken out because because let's say Maria's the first one, then in the next branch, yeah, Maria can't be part of the last.
Unless.
Yeah, she's not one of the options because she was already chosen in the first.
Order.
In the first.
All right.
You know, there's a way of thinking about it where you have like pairs and then you widen it and then you widen it, you know.
What?
But if you have to.
I would just look at it as, since order doesn't matter, it's just, I would just do 5 NCR2. 5
Why don't you
choose
just do, there's 5 of them, and then each of them has the option of being with the other 4, so 5 times 4 is 20. Is that what it is?
It's
but
not
the answer's
20
10.
now.
It's
It's
divided by
it's
10
Yeah.
handshakes. It's like you have 5
Oh, so you
different
divide it by
pairs.
2. There's
How
only
did you
2.
deal with this?
You divide it by 2 because whether they're the first or the second doesn't matter. You cut it in half because otherwise it's repeated.
Okay, I get it.
But the addition
So-
way makes more sense. if you
The
think
addition
about
way,
it.
exactly, it makes more sense that the first person can be with 4 others, then the next person has 3 other partners, the next person only has 2, the next one only has 1 because he's already been with everybody else. So that's why there's 10 ways.
Technically, you can't.
Find the probability that both Maria and Susan will go on the trip, and what's 1 out of 10? Okay, it's only
Okay.
1 out of 10 ways that they'll both go on the trip. All right. Let's look over at some non-calculator questions like this.
Distributions is fun.
Go to the last page of actual questions. Okay, it says number 24, that's what you're looking at, the probability of obtaining heads. Because then it gets into just answers. All at once. You see the question I'm looking at?
Yeah.
It says number 24. The probability of obtaining heads on a biased coin.
What does that mean?
I
It's
mean,
1/3.
Said unbiased.
bias,
Yeah.
you know,
Bias means it's not, it's not just that it's more likely to happen on one side than the other. It's a weighted coin, it's a trick coin or
It's kind
something
of
like that.
redundant to say biased if you've given third.
Right. But they're giving you that, they're telling you it's biased, and then they're telling you how biased it is.
Yeah.
Sammy tosses the coin 3 times, find the probability of getting 3 heads.
127.
127.
Oh, yeah.
Yeah, but 33.
1/3 times 1/3 times 1/3. 2 heads and 1 tail.
627.
1/9.
627.
Why don't y'all argue and tell me why?
But it's the same thing as before, wouldn't it?
Yeah,
It
so
would
it's,
be-
it's 1/3 times 1/3 times 2/3
Yeah.
times 3.
wait. Oh,
What?
Yeah, times
I
3, you have to
forgot
do that again.
Yeah.
Why do we have to do times 3?
There's 3 different ways.
Yeah.
There's 3 different ways.
Yeah.
It can be head, head, tail, head, tail, heads, tail, head, heads. So you would do 1/3 times 1/3 times 2/3 times 3. Okay, so it'd be 2/9. Right? Alright. Amir plays a game in which he tosses the coin 12 times. Find the expected number of heads.
4.
So we're talking about expectation. It's just the number of times you're doing it times the probability. So it'd be 4. 12 times a third. Amir wins $10 for each head obtained and loses $6 for each tail. Find his expected winnings.
-8.
We'll take the outcome, which in this case would be 10 times the probability, which is 1/3, plus the outcome, which is -6 times the probability, which is 2/3, right?
Yeah.
And then you get your answer. So this is 10/3 minus 12/3 is -2/3. Okay? What?
Times 12.
No.
Yeah.
Calculation just makes it so complicated.
Find his, oh.
Oh, he does. Wait. Plays the game which tosses the coin 12 times.
Yeah, times 12.
Sure. Times 12.
Could you do
Which is negative
10
$8.
times 4,
Yeah.
and then
Yeah.
-6 times?
You could.
Yeah.
Yeah.
That'd be easy.
That
would be more
That's the easy way. I wasn't paying attention to the 12 flips. I was just thinking on every flip, what's his expected outcome? Because that's usually expectation problems. Calvin.
No, I realized I had my hand up and then I was like, why not?
All right, so obviously we haven't looked at every possible type of probability problem, but that's some. Now let's talk distributions. Okay? We've got about a half hour left from when I said I would say, so, or 25 minutes or whatever. Binomial distributions.
Those are
Which
fun.
one are we doing?
Fine.
We're not looking at a problem yet, just wait. Binomial distributions is when you have 2 outcomes and only 2 possible outcomes. All right? We usually think in terms of success or failure. Yes, no, true, false. Okay? The questions that can be asked could be, often it's a manufacturing situation where a product is produced, 3% are found to be faulty. In a batch of 250, what's the probability that 6 are faulty? What's the probability that less than 5 are faulty? What's the probability that more than 12 are faulty? Those types of questions, right? Where we're given a probability of success, all right, and then we're told a number of trials. You have usually a P, which is your probability of success. Now, from that, you can always calculate Q, which is what? Probability of failure, which is just 1 minus P.
Better just like P apostrophe.
You could, yeah. Just usually, I don't know why we use Q, but it's P complement.
Yeah.
It's 1 minus P, but usually P and Q. And then N is the number of trials, right? Meaning the number of things we're looking at. So, on the calculator, let's look at the calculator for a minute. You've got binomial, it's under stat, calculate. If you scroll down, you've got 2 of them there. I'm in the wrong, where is it?
You can just go to
It's in the
catalog.
catalog.
Yeah.
Second,
Yeah, it's-
second 0.
No, I'm sorry, it's in distributions. I don't know why I said stat. Second, distributions. You all haven't looked at that?
We did
Right.
catalog.
Second, we
We did it from the
catalog.
catalog?
Yeah.
Yeah.
Where's the
That's
Don't do
only
it from the
sheet.
catalog.
History.
Where's the
You see where it says
Bars.
variables? It's
Yeah.
distributions.
Oh, well, that would have been a
I
lot
lost
easier.
straight by everything.
Like, a lot
I know,
easier. But this is a lot quicker.
Yeah, and they're all together here. All right, you've got 2 binomial things there. You have binomial PDF, which is the probability density, probability distribution function, and binomial CDF, which is the cumulative distribution function. What the cumulative does is it adds up, if you put in up to 2, then it'll add the probability for 0, the probability of 1, and the probability of 2 all together. It'll add it for you, right? Or if you want to know greater than 2, you would do 1 minus up to 2, right? So it's a cumulative thing. The binomial PDF is at a specific number, okay? So the way you enter this, and it's been a while since I've done it, and I don't have the type of calculator here that I want. Who's got a new one? Let me throw that up here real quick because it's going to look different, and that's what I want anyone watching this to see, and that's what you guys need to know on your test. All right, the number of trials, the probability of success, and then X, which means we're looking for how many successes, okay? Now, don't get thrown with that word success, because a success might be a broken machine. That may be what we're deeming a success in this instance. Whatever P is, whatever that's the probability of that happening, this is how many times that's going to happen. That's what we're looking at here, okay? So, we'll make up a problem real quick. Let's say,
500 machines.
well, yeah, we're making 500 widgets. The probability that a widget is bad is 0.03.
That's 0.03%, or do you type in 3 for 3%?
30%.
This is 3%, 0.03, okay? And then what's the probability on any given day that 10 of them are faulty?
15.
Well, the answer is 0.0479.
She raised like you
We
guys
had to,
like
like-
memorize how to put each one in separately.
But so
We
during
have
our
to do, like,
exam,
lower
we,
value, upper value.
That's
median,
not
standard.
binomial.
No,
That's normal.
Oh, yeah, yeah.
That's normal. We're not
So-
talking normal yet.
on the
Oh, yeah,
exam,
yeah.
we will have that system.
Because you have to do what they did.
So I don't have to memorize what I had to plug in. Okay, that would have been a lot helpful. I was like trying to memorize it. 'Cause I-
Catalog Help would have told you how to do it anyway, though, even with the other system.
That's,
No, it doesn't.
It doesn't,
I
not
have
with
the
this
new
one.
and it doesn't do
Catalog
gave
Help
the-
doesn't do any good on the new one, though.
We're gonna take the percentage.
The catalog.
But our
is
exam will do that
it-
system.
I'm not talking about catalog.
God.
I-
You never use catalog. Okay? Don't ever use catalog.
wait, if you had, here,
It's in alphabetical order.
if you had, in a given day, let's say you had 500 machines, it was 10% that one would be broken, wouldn't you have a 100% chance that 50 are going to be broken that day?
No, that's not guaranteed.
No, because you might have none broken.
Yeah. It's never guaranteed.
So, but it's the most probable.
She had 900.
That, your probability that something's broken, that data, or that statistic is taken from data collected over time. Most likely, it's an experimental probability.
Yeah.
So based on the last 10 years worth of days, this is the most likely result, is that we will, or we can predict based on those 10 years worth of days that we will have that much. But on any one given day, there's no guarantee that anything will break or everything could break, right? Now, so a company is then going to have a probability of success that every year they're going to reassess what that probability is based on that year's data. Or if all of a sudden, if we expect to only have 3 or 4 broken things and we're having 100, then as a company owner, I'm going to figure out why are they all breaking. Is it user error? Is it machine error? Is it they're not sweeping the dust out at night? Right? All sorts of different things. But we realize that nothing's going to be perfect, but when you start having a lot of variance is when you start to look and see why. This is binomial, not normal, so you don't need upper and lower. This you give us specific,
What
okay?
is that number in our little situation?
This is the probability that of the 500 trials or 500 things we're making that day, when we know that 3% of them are going to be bad, this is the probability that exactly 10 of them are bad.
Okay.
Okay? How would I give the probability that less than 10 of them will be bad? Well, now I'm going to go distributions CDF from 500 trials, still the same probability, 3% that are bad. And I'm saying less than 10 are bad. Then what am I going to put in here? 9. 9 is my X value. Because what is less than 10? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Okay. If I say at most 10, then I would put 10 here. Right? But if it's less than 10, I put 9. Paste it. So there's a 6.69, yeah, 6.69% chance of that, okay? What if I said at least 10?
11.
One minus.
1 minus.
Yeah, because it can only, the calculator can only calculate from 0 up, right?
Right.
So if it's at least 10,
Before the 10.
okay, it'd be 1 minus this, right? Because at least 10 is the opposite of less than 10, right? So 1 minus this answer would be at least 10 of them are bad.
Is there a reason why there's no equation without, like, is there a reason why the binomial numbers don't work